Hi friends, this is Mr. Zarzak, and in this screencast I'm going to give you some information about Newtonian gravity. Alright, so let's get going. So Newtonian gravity, alright, starts with Newton and Newton's famous thought experiment. So it goes like this, alright. He says here, let's take a cannon and put it on the earth, not to scale, alright. If we were to fire a cannonball, alright, a cannonball would follow that arc of a parabola and it would crash into the ground. Okay, well, Newton says, what if we could fire it fast enough to where the curvature of the Earth would start to come into play? The cannonball would travel a longer distance. The Earth itself would curve off. And so what would happen is that the cannonball would be in the air for longer than it would be if we just fired it horizontally along level ground, because the ground would literally curve away. Okay, so Newton comes up with this idea. He says, would it be possible to fire the cannonball fast enough to where the arc of that parabola winds up matching the curvature of the Earth, in which case the cannonball would go all the way around the Earth or orbit the Earth. That word orbit, there's a Latin origin there. It really means to circle around. Okay, so let's back this up a little bit. Okay, why does it arc in the first place? Why? Because it's pulled on by the force of gravity. Okay, so it would like pull it down, right? It pulls the cannon, pulls the cannonball. Okay, well, let's say that at some point later on, our little cannonball, which starts off from the cannon, is over here. All right, well, that means it just gets pulled down, but down is a different direction over here. So the force of gravity acts over here. Okay, and when the cannonball gets over here, it would be pulled in this direction downwards. Okay, so like down changes depending upon where you are. What's important is that force of gravity always seems to point towards the same spot, which is the center of the Earth, which is its center of mass. As the cannonball moves around, okay, if it can achieve this speed, it will not fall into the Earth, but will fall around the Earth, and it will orbit. Now, of course, there's all kinds of problems with this. You have air resistance, and then even if it could make it run back into the cannon and make it explode. Okay, but just a thought experiment, so just kind of bear with me. Newton knows that gravity on Earth's surface is 9.8 meters per second squared, okay? And so he says, all right, well, if it's gravity that's causing this centripetal motion, we can write an equation. All right, this force of gravity causes the cannonball to accelerate centripetally. Now, of course, we know that centripetal acceleration is just v squared over r. All right, where r would just be literally the radius of the Earth. Okay, in Newton's time, the radius of the Earth was also very well known. All right, so I looked it up, and it turns out that the radius of the Earth is 6.371 e to the 6th meters. All right. So what would that be? That'd be 6,371 kilometers. Okay. Well, anyways, the force of gravity causes the cannonball to accelerate around in a circle. Okay, that's our weight, which is mg. mv squared over r. Notice the mass here just factors right out. Okay, we know what g is. It's good old 9.8. All right, so if we know that, well then, and we know the radius of the Earth, well, look what we can do here. We can say g times r is equal to v squared. Take the square root of that. All right, and so if we take the square root of 9.8, all right, times this 6.371 e to the 6th. All right, that'd be 9.8 meters per second squared times 6.371 e to the 6 meters. So we have meters squared per second squared square rooted, so we get meters per second. Great. Okay, we throw that into our calculator, and we get this number spit back out. 7901 meters per second, which is approximately 8 kilometers per second. Okay, if we could fire a cannonball at about 8 kilometers per second, the cannonball will orbit the Earth. All right, now that's pretty fast. All right, we don't have cannons that shoot that fast. Okay, the way that we get things going that fast is we strap them on top of really, really, really big, powerful rockets. Okay, that's really what rockets do is they get you going fast. They'll get you above the atmosphere where there's no air resistance or a pretty minimal amount of air resistance for low orbit. But really what they're doing is getting going fast enough so that when you run out of rocket fuel, instead of falling back down into Earth, you fall around the Earth, okay? Well, anyways, so Newton comes up with that. Oh, that's curious. That's interesting. What else can we do with that? Okay, so Newton ponders the moon. The moon goes around the Earth in a much, much bigger path. Let's see, so if I was going to draw that path of the moon, I don't know if I have enough room. Okay, so there we go. It's a perfect circle. Yeah, right. Interestingly enough, by Newton's time, so this is early mid-1600s, okay, the distance to the moon was very well established. The Greeks worked this out in like 1500 BC. It was a really, really long time ago. The distance to the moon proportional to the radius of the Earth or the moon, the distance is much bigger. Okay, so I looked this one up too. Okay, so the distance out to the moon, okay, is, what is that, 3.84 e to the 8th meters. Okay, so much bigger order of magnitude than the radius of the Earth. It turns out if you throw the radius of the Earth and you divide that in the radius of the moon, it's about 60 times the distance. Okay, so like the distance from the Earth center, okay, to the surface, okay, that radius of the Earth, okay, that's about 1/60th the distance out to the moon. Okay, that'll come back, that'll become important in just a minute here, so just remember that, all right, that this radius of the moon divided by the radius of the Earth, okay, gets you approximately a value of 60, okay? Well, anyways, what else do we know about the moon? Well, for forever, people have been tracking the moon and using it as a way of keeping track of time, okay? So it takes the moon about a month to orbit the Earth once. It's not exact, all right, but you can pay attention to this, and what you do is you pay attention to when the new moon shows up, and that occurs once every 27.3 days. Okay, so we said that's the orbital period of the moon. It's how long it takes to go around once. If we were going to take and we could convert that, so let's see, so for there's 24 hours for every 1 day, and then for every 1 hour, there's 60 minutes. And then for every 1 minute, you got 60 seconds. Okay, so if we took 27.3 multiplied by 24 times 60 times 60, okay, we could get the orbital period of the moon in seconds, which works out to 2,358,720 seconds. Okay, if you don't buy it, well then next time there's a new moon, start counting, okay, and get up to 2,358,720, and then you should see another new moon again. Great. Okay, so what? Well, from this we can figure out actually how fast the moon is actually moving around the Earth. This is pretty neat. All right, so if we start with just a simple idea that, like, speed is just distance over time. Okay, well, the time period, that's that period. That's 2,358,720 seconds. All right, the distance that we travel, well, we're moving along a path that's approximately a circle. There's a little bit of an ellipticality to the moon's orbit, but for our purposes, we can approximate it as a circle. So now look at this. This is kind of neat. The way that you calculate the distance of a circle, right? There was a circumference, so that'd be like 2 pi r. So if we just do a little substitution, we replace d there, the distance that it travels is with 2 pi r, where this r is the radius of the moon. Okay, and we divide that by the time period. Okay, well, from that, we can work out how fast the moon is moving around the Earth. It winds up being somewhere 1,000 or 1,100 meters per second. Okay, it's pretty quick. I'm not going to do that calculation because that's not really what I'm interested in here. Okay, what I'm interested in is Newton's idea that the Earth's gravity was what was causing the moon to move around it. His idea was that maybe the moon was falling around the Earth in the same fashion that Newton imagined that a cannonball fired fast enough from a cannon would fall around the Earth and achieve this thing that we call orbit. Okay, so that's really what we're more interested in. So from that, here's what he does. He says, okay, great. So this would be how fast the moon would be going. It's 2 pi r over t, all right? The moon is experiencing centripetal acceleration, right? It's turning around the Earth as it moves, okay? And centripetal acceleration is just this v squared over r, where again, the r now is just this radius of the moon, okay? So if we do a little bit of substitution here, look what happens. So we get this centripetal acceleration. So we get 2 pi radius of the moon over t, and that gets squared, divided by the radius of the moon. Okay, so we're just subbing in for v squared over r. All right, so let's see. So what do we have here? So 2 squared is 4, pi squared is pi squared. So then we'd have the distance to the moon squared over period squared over radius of the moon. Okay, so we can factor out a little bit. So we just get rid of goodbye, goodbye. Okay, and I'm running out of space, so I'm going to jump over here and write this. So the centripetal acceleration of the moon. So we get this 4 pi squared. Oh, and I made a math mistake. Wait a minute. Hang on. Hold on. I got it. Dividing by a fraction. Oh, rookie mistake. Can't factor that out. That actually makes it bigger. That's kind of funny. So we take that radius of... Oh, no, I was sorry. I was right the first time. It's late. I'm tired. Cut me some slack. All right, so let's see. So we get the radius to the moon divided by that period squared. All right, now if this isn't some fun calculator work, I don't know what is. All right, so let's go ahead and actually calculate this. So we get this 4 pi squared. We take this distance to the moon, so we get 3.84 e to the 8th meters. Okay, so 4 pi squared r divided by the period squared, which is this 2, 3, 5, 8, 7, 2, 0, and then we take that number and we square it. All right, throw that mess into your calculator if you do it correctly. And if I haven't made any math mistakes, come on, physics gods, stay with me. I should get 0.00272 meters per second squared, okay, which is a really small number. All right, the amount of acceleration, the amount of turning that the moon does, okay, is extremely small because, well, the circle that it makes is so big. Okay, the amount of curvature of that circle is just really, really tiny as it moves through. Okay, so anyway, so Newton actually calculates, he figures all this stuff out by hand, and the real genius, okay, behind this is he looks at this and says, hey, there's something going on here. Okay, he had originally guessed that the moon is 60 times farther from the Earth than we are, right on the surface of the Earth. Okay, so his guess was that gravity got weaker with distance. Well, the funny thing is if you take 9.8 and you divide it by 60, you do not get this 0.00272. Okay, however, if you take 9.8 and you divide it by 60 squared, you do get this 0.00272 meters per second squared. Okay, and why is that important? Well, Newton realizes that the effect of gravity gets weaker with distance squared. He had discovered the inverse square law of gravitation, okay, which is kind of unbelievable that he thought up all this from nothing. All right, he says, great. The effect of gravity, all right, the force of gravity is proportional. So that little symbol there means proportional, okay, to the 1 over the distance squared, or how far away you are, all right, from the object generating the gravity. He says if you're on the Earth, you're being pulled on by the Earth. That's the force of gravity due to the Earth. All right, he also says the Earth has mass. The moon has mass, okay? Excuse me. The Earth is pulling on the moon. The moon is pulling on the Earth. They must be pulling on each other because of Newton's third law, written by Newton. Okay, so there's an interaction, a force interaction. The moon must have less mass than the Earth because we can see the moon going around the Earth and not the other way around. Now, the reality is that they technically orbit each other. The Earth wobbles around, okay, as the moon is in orbit around it. That's a conversation for another time. Okay, they've got a common center of mass, blah, blah, blah. All right, but what's important is that Newton has come up with this idea, all right, that the force of gravity is proportional to the two masses and inversely proportional to the distance between the two of them squared. Okay, this is Newton's idea about gravitation, which we now know as Newton's law, universal law of gravitation, all right, which I have written down here. Okay, there's that little proportionality constant. Okay, Newton was never able to figure out the proportionality constant, which is a fancy way of saying is if you take the mass of the Earth and multiply it by the mass of the Moon and you divide it by that distance between them squared, you don't get the force of gravity between the two. And if you take your mass and the mass of the Earth and you multiply those two together and you divide that by the radius of the Earth squared, you don't get your weight in newtons. Okay, so Newton says, hey, the equation doesn't work, but it's not because it's conceptually wrong. It's because there's some number. Yeah, it's some multiplier. Okay, so some fudge factor. It's kind of like if you're working a physics problem and you just can't get it, and your buddy's like, hey, if you just multiply it by 2, okay, then it works, and you do it, and you get the answer right, and you want to go to bed, kind of like I do right now, and you don't really understand why, okay, it works. Well, Newton is kind of fudging, but he's Isaac Newton, so of course when he says that there's some fudge factor that makes it work, well, then there is, okay, and that G is what we now know as the universal gravitational constant, okay, and it's this number here. We've got it measured out to more digits now. This parentheses shouldn't be there, and this should not say thought. It should say, though it is still the least accurately known universal constant. Okay, so even though we've got it out to, like, I think it's five sig figs right now, it's such a small number. It's crazy that it's actually still not even that precise. Okay, but it's good enough for us to do calculations with, so you kind of need to know that one. It's on the AP equation sheet, but it's just one of those ones where it just kind of gets stuck in your brain after you use it enough. Well, anyways, so we get this formula, this universal gravitation, this Newtonian gravity formula. Okay, once we've got it, there's all kinds of fun things that we can do with it. Right? So, I don't know about you, but when I was a kid, I used to like to play in the sandbox, and I always wanted to dig a hole through the earth to the other side, and I never made it. No one ever has. We haven't even come close. All right, but as we would dig through the earth, some interesting things happen. Okay, so a couple things I want us to consider. All right, one is what would happen if we could hollow out the earth? So if we made the earth like an empty shell like this, where we concentrated all the mass of the earth, okay, into this kind of spherical, I don't know, this hollowed out orange or something, okay? Well, Newton's idea about gravity is that gravity is mass pulling on mass, all right? And so if all the mass of the Earth were concentrated near the surface and you dug down into this hollow shell of an Earth, okay, well, you'd be pulled upon in all directions, okay, by all parts of this mass that's above you. Now, the mass that was the closest to you, okay, would pull you much harder, okay? So just think like this force of gravity is equal to G m1 m2 over r squared, okay? So the closer you are, the bigger the force. So the stuff that was directly above you would pull you with a lot of force, okay? The stuff that was below you, all right, it would pull you with less force. So I'm going to try to make my lines a little thinner here just to kind of represent this, all right? But there'd be proportionally more of that mass below you, right? So like this stuff here, would pull you like up and to the right and up and to the left. Overall, the effect of this, all right, is we get this like upward kind of pull. That's a terrible color to pick. Here, I'll just use some red. We would get this overall upward pull, okay? The left and the right part would cancel. Okay, and down here you get this downward pull, okay? And you'd have more things contributing to it. Okay, well, it winds up, all right, that if the Earth were hollow, okay, all these force vectors would cancel out and you would be effectively weightless no matter where you were, okay, inside the planet. Okay, it might be a little bit easier to imagine it as if we took you and we put you right in the very center. Okay, you'd be pulled simultaneously with equal amounts of forces in all directions. You'd be in equilibrium. Okay, well, no matter where you would be, as long as you stayed inside this shell, you'd be in equilibrium. Okay, and that's if we could hollow out the shell, and that's an important concept that we'll use when we get to electrostatics second semester. So kind of keep that in the back of your mind. All right. Well, the Earth is not hollow. So what if we tunnel down? Okay, so like imagine like starting at the surface here and we like dig our tunnel down, okay, to this location. All right. Now I've got two different colors just to represent, okay, the different layers. So like the lighter yellow that I have here, this would be kind of like the shell of the Earth that would be above this, all right? This is not to scale. You'd be like super duper teeny tiny. Okay, so like all this stuff here, is kind of analogous to like I'm inside the shell here. Okay, so think like all this mass that's above us doesn't contribute anything at all. Okay, it's really just the mass that's below us, okay, that winds up pulling on us, right? So like the mass that's directly below us pulls us down, the mass that's below us to our left pulls us down and to the left, and the mass that's pulled down and to the right of us pulls us down and to the right. Okay, well, the overall effect of that is we get this combined force, this downward force that we call gravitation. All right. The thing is that, well, as we dig down, all right, the amount of mass of the Earth that's below us gets proportionally smaller. The stuff that's above us, okay, that actually acts just like that hollowed out Earth. That stuff that's above us keeps us in equilibrium. The stuff that's below us gets us this net force towards the center that we call our weight. So the point is as we dig down, we weigh proportionally less, okay? Now, what's really interesting about this is the way that our weight would vary as we would move down to the center of the Earth, okay? Now, I put a little note about making reference to the video. There's a Minute Physics that's probably going to do a better job at this than I am, but it's worth talking about, okay? So just kind of oversimplified, our weight is due to this gravitational constant, our mass, the mass of the Earth, okay, divided by how far we are from Earth center squared, okay? Our weight is mg. That's like the little mass. Big G, m1, m2 over r squared. Now, of course, we all weigh different amounts, okay? So, but the real constant is the effect that we feel from gravity. It's at 9.8, all right? And we think about that as meters per second squared, but you can think about that as newtons per kilogram as well. How many newtons per kilogram of mass? So how much force we get for every kilogram of mass. Our mass doesn't even matter. Okay, so we can get this G, mass of the Earth, divided by the radius of the Earth squared. Okay, by the way, if you looked up the mass of the Earth, multiplied it by that universal gravitational constant, and divided by Earth's average radius squared, you get 9.8. Okay, well, anyways, imagine the Earth as having uniform density. Okay, so now that's not true. Okay, the Earth has different layers too, but it just makes it easier to conceptualize the problem. All right, so if we say that this symbol here, so this is Greek letter sigma, would be like the density of the Earth. Okay, well, you might remember from chemistry or like a physical science class that density is just the ratio of mass over volume, okay? So if I take and I move that volume over, if I take density and I multiply it by volume, okay, I can also represent mass this way, okay? Well, if we assume that the Earth has approximately uniform density, and we also approximate the Earth as a sphere, it's pretty spherical. It's not a perfect sphere, okay? It's actually a little bit thicker towards the equator because it's spinning, but again, okay, we're just simplifying here. The volume of a sphere is 4/3 pi r cubed, okay? So that's a way that we could represent the mass of the Earth, all right? Well, there's mass of the Earth. Here's mass of the Earth, too. So we'll call that M2 just to stay consistent. All right, well, look what happens when I sub in here. Okay, the effect of gravity is equal to G, all right, times the mass of the Earth. So we're going to put in this density times 4/3 pi r cubed. Okay, so there's your GM over r squared. All right, now notice r cubed in the numerator, r squared in the denominator, factor. Okay, and we get this. All right, so I'm going to bring the 4 pi out in front. Okay, I didn't forget about that 3, so just hang on. Times the universal gravitational constant times the density of the Earth. All that divided by 3. Okay, so all that stuff, the universal gravitational constant, the density of the Earth, 4 pi and 3, those are all just values. Those are just constants. Okay, times the radius. All right. So what are we looking at here? We're looking at directly proportional. That's what we mean. All right. So as we would tunnel down into the Earth, let's say that we went from the surface of the Earth halfway to the center. Okay, so we'd have half the radius. We get half the effect of gravity, which means we would weigh half as much. If we went 3/4 of the way to the center so that our distance to the center of the Earth was only 1/4, well, then we'd only weigh 1/4 as much. We'd only feel the effects of 1/4, 9.8. Isn't that neat? And then look at this too. What if we went all the way to the center? Well, if that distance goes to 0, well, then the effect of gravity goes to 0. So it's like if we could climb down a ladder to the very center, we'd be pulled in all directions. And we'd be effectively weightless. We could climb down a ladder and step off that ladder and we would float. There would be no up or down. Okay, there would just be equilibrium. How neat is that? All right. So those are just some of the things that we've learned about gravity. There's lots more, but, well, that's enough for one video. So I'll say thanks for watching, and we'll see you next time.